materials. And before I continue to introduce Professor Hassan, who was a student of Professor Professor Al-Qadi, do you want to say a word?
Yeah, absolutely. First, I wanted to thank you, Lama, for inviting Marwa. We are very, very pleased to have her with us here. I mean, we go way long, at least maybe 22 years, but I'm still young, and she's much, much younger than that too. At Virginia Tech, I have worked with Marwa as well as her husband. I get the pleasure of meeting the whole family. She is an amazing person. The most important thing, so I will not take from the talk, is that she was able to establish an amazing program at LSU, and she's leading now the UTC. She's definitely found a great position for herself in the transportation field. So, Marwa, a personal note, I'm very proud of what you have accomplished. We're very, very pleased to have you with us here today as a keynote speaker. So I turn it back to Lama.
Well, Professor Hassan is the director of the Regional University Transportation Center, as well as the CETF Distinguished Professor and Jacobs Professor of Excellence at Louisiana State University's Department of Construction Management. She holds a doctoral degree in building construction from Virginia Tech, a master's in civil engineering from Cairo University, and a bachelor's in construction management from the American University in Cairo. Hassan's areas of expertise are evaluation and characterization of sustainable infrastructure materials and life cycle assessment. She has more than 20 years of industrial and academic experience. We're so happy to have you here, Professor Hassan. Just a few quick reminders for everyone. The presentation will go on for 40 minutes, followed by 20 minutes of Q&A. You can either raise your hand and we'll allow you to ask your question yourself, or you can simply type your question in the chat box and we'll ask it on your behalf at the end of the presentation. So without any further delay, Professor Hassan, please, the audience is yours.
Thank you so much, Lama, and I cannot thank Dr. Al-Qadi enough. He has been a mentor and a father and a big brother to me and to my whole family. So I really appreciate the invitation and I'm so glad to be here. And with that, I'll start sharing my screen. Can everybody see the screen?
Yes.
Perfect. All right, so today I'm going to talk about innovative infrastructure materials. Before I talk about the research, I just would like to give a quick introduction about transit. So what is transit? It's a university transportation center that services Region 6. Our main theme is solving emerging transportation resiliency, sustainability, and economic challenges through the use of innovative materials and construction methods. And we don't just focus on research, but we take it all the way to implementation, as I'm going to show you in a second. We are a consortium of 11 institutions, 9 universities and 2 community colleges that are in all of these states: Texas, Louisiana, Arkansas, Oklahoma, and New Mexico. These are some of our metrics right here. So as you can see, we have funded to date 99 projects that total $13.6 million. We have partnered with a lot of external agencies and they have contributed an additional $1.7 million. Out of these 99 projects, 27 were collaborative, and we developed a lot of new technologies, 123 to be exact. We cover a lot of socioeconomic areas that relate to transportation, including metropolitan growth, future transportation challenges, declining public revenues, underserved and underinvested communities, and safety. We also don't just focus on research. We work in education, workforce development, and tech transfer. So these are some of our major accomplishments in terms of education. We hosted or participated in 73 STEM events. We developed 136 new educational modules that are either standalone and web developed or part of existing classes in the 11 institutions. And we've supported over 406 graduate and undergraduate students. With respect to tech transfer, we host webinars on quarterly basis. To date, we have hosted 28 webinars. We also post all our publications, whether they are reports, presentations, or journal publications on our website. And we look at the downloads, and as you can see, we have a large number of downloads. With respect to workforce development, we host professional society related events and we participate in them. To date, we have participated in 182 events, and we also host seminars and workshops where we educate the industry on new technologies developed or focus on solving different challenges together. We want to make sure that we are performing up to standard. So we have center metrics and we continuously monitor them. This is a snapshot of some of our metrics. With respect to tech transfer, we look at the number of commercialized or patent or licensed research projects, and to date we have 21. We also look at the number of memorandums of understanding that we sign with our stakeholders, and to date we have 19. With respect to education, we look at how many students are actually benefiting from our educational modules. So we look at the number of views, and we have almost 4,000 views to date. And how many students participate in our STEM events, and we have about 3,300 participating to date. As for workforce development, we look at the number of people who attended the workshop, and we ask them for feedback by filling surveys. And we have about a little over 10,000 that have attended our workshops and seminars to date. We also look at how many of them, our stakeholders sponsor our events and how much have they contributed. And we have 47 sponsors and they have participated a little over $400,000 to date. As I said, we don't just focus on research, but we also focus on implementation. So this slide shows just some pictures of different implementation projects that we have to date. So right here, these are implementation of pavement markings in a pavement marking project. And here, this bridge is constructed with ultra high performance concrete that was developed in New Mexico. And right here is actually the road in front of our College of Engineering building at LSU. And this mix is developed by us. And I'm gonna give a presentation. So part of my talk is going to be about ECC, but this is low-cost ECC. And the funny part, and I'm sure Dr. Kadi will get a laugh out of this, this is not a competitor to concrete. This particular mix is an actual competitor to flexible pavements. It has a very low compressive strength, but an extremely high ductility and flexibility. And so it behaves like a flexible pavement. And it has been in place for a year and a half and with heavy bus traffic, and it's performing very well, not a single crack. In addition to this, we do a lot of many more activities. So this picture just shows some of the activities. If we look at this top picture right here, this was an event that was sponsored by Prairie View EMU, which is a historically Black institution that is part of the consortium. And they were exposing their freshman students to the field of transportation to increase the participation of people of students in transportation. This event included more than 70 students. The second one is an actual implementation project that resulted from a transit project, and it was led by University of Texas at Arlington. They are currently doing a full depth repair using ultra high performance fiber reinforced concrete at the Dallas-Fort Worth airport. And it saved them over $1.5 million just because they didn't have to close the runway for a long time due to curing of concrete. The third picture is from Arkansas State, where the students participated in an artificial intelligence demonstration. 30 students were featured in this demonstration. The one on the left side at the bottom is an event that was hosted by Dr. Zahid Hussain and his students. They hosted an event for the industry, the DOTs, to show them or to educate them about their flowable fill concrete, the FCC mixes. And this event was attended by 40 stakeholders. The one next to it took place in the Arkansas State Museum, where a group of students participated in the Tinkerfest STEM event, and more than 1,200 visitors were part of this event. The last picture promotes or presents one of Dr. Al-Qadi's students as well, or at least he was a postdoc with Dr. Al-Qadi, Dr. Samer Dessouqi. He was awarded the ITE's Transportation Achievement Award for his design of the Highway Integrated Sensing and Energy Conversion Module, HISAM. This is a quick introduction about transit and what we do. And of course, we collaborate with a lot of other centers. And I would love to collaborate with ICT as much as possible. So now I'm going to start talking about research, and I'm going to talk about innovative infrastructure materials. And here the focus goes more into our research group at LSU and our partners that work with us. We, over the years, have developed a lot of sustainable technologies. So we focus on introducing new technologies that can enhance the sustainability, resiliency, and durability of the infrastructure. A long time ago, we developed photocatalytic pavements. If you don't know what that is, it's a pavement that has nanotitanium dioxide that is capable of absorbing pollutants like VOCs, NOx, SO2s that are produced by the traffic car mufflers, and neutralize them into salts that are washed away by rain from the surface of the pavement. We had the first field studies in the US that tested both asphalt and concrete photocatalytic pavements. This picture is from a product that we developed where we recycled a beer glass, like glass cullets, in asphalt shingles. And we designed a new generation of shingles that can be a solution to the urban heat effect. And we actually applied for a patent for this technology. This is self-healing concrete, and we have a lot of work going on in this area where we heal concrete with microcapsules that contain chemicals that can produce calcium silicate hydrate, so heal concrete with concrete. We also do a lot of work in bacteria self-healing concrete. The lower three pictures represent the technologies that I'm going to talk about today. So we developed low-cost and ultra-high performance ECCs. I'm going to be talking about the low-cost ECC today. We also developed a new generation of material called engineered geopolymer composites, and they are metakaline based and fly ash based. And we also developed self-healing asphalt, or self-rejuvenating / self-healing asphalt, which I'm also going to talk about today briefly. Okay, so let's start with the low-cost engineering concrete composites, ECCs. There is a saying, if it isn't cracked, it ain't concrete. So we drive around all over and there are cracks everywhere in the concrete. Concrete is a very important material that we utilize not just in our pavement or even the infrastructure, but even in our commercial buildings, etc. Unfortunately, it's a brittle material, so it's prone to cracking. It also has permeability that increases over time, which allows the litter substances to enter into the structure of the pavement, causing damage and lack of durability. In addition to all of this, concrete expands and contracts, and it has a high coefficient of expansion, which means we need joints in order to avoid cracks. But these joints are a major deterioration mechanism. So we see things like joint faulting, spalling, corner breaks, etc. One solution to a lot of these problems is the ECC. So ECC is not new. It has been developed about a couple of decades ago by Dr. Victor Lee from the University of Michigan. The main advantage of ECC compared to concrete is that it exhibits pseudo-strain hardening after cracking. This leads to an increase in load carrying capacity with a significant increase in deformation, which allows us to produce bendable concrete like you see right here in this picture. So how do we design ECC? There are two basic criteria that must be met for successful design of ECC materials, what we call the strength criteria and the energy criteria. The strength criteria warrants adequate fiber bridging capacity upon crack initiation, where the energy criteria guarantees the occurrence of the steady state crack propagation. The strength criteria require that the minimum fiber bridging capacity, sigma node right here, is larger than or equal to the matrix cracking strength, which is sigma critical. The energy criteria require that the complementary energy of the fiber bridging relation, which is JB right here, is greater than or equal to the crack tip matrix toughness, J tip over here. The design of ECC is based on fracture mechanics principle. Sigma critical and J tip are controlled by the cementitious matrix, while sigma node and JB are controlled by the fiber matrix interface. Both criteria have to be satisfied for us to get the pseudo-strain hardening behavior. And I'm going to talk about that more in a second. Okay, so if ECC is so good, why is it currently not being used? And it's because ECC has limitations. It's very expensive. And that's one of its most major limitations. It also has a high environmental footprint because it uses a lot of cement. And it's not practical compared to regular concrete in terms of we have to put a lot of fibers, and they are specific fibers, oil-coated PVA fibers, according to Victor Lee at 2% volume fraction. So that much fiber needs special mixing requirements for good dispersion. So it's not everybody can install it properly on site. So that's why it has not been advancing as quick as we had hoped. When we started this research, we said, can we solve these problems? And we started looking at low-cost, green, and readily available ingredients that can replace some of the components of the ECC, so we can actually produce ECC that can be used in the field. So we focused on a number of things, developing low-cost ECCs. We started testing or developing mixes that can work with non-coated PVA fibers to reduce the cost of the fiber. We also reduced the fiber volume fraction from 2 to 1.5 and 1.75, and we got that to work. Another ingredient that's expensive in ECC is microsilica sand. It has to be very round, very soft, very small, fine sand. So we replaced the microsilica sand with locally available materials that are present in Louisiana and in Region 6. And we started replacing some of the cement content with high fly ash class C content. And we also experimented with using recycled content from chrome rubber. We developed mixes that work, and I'm going to show you snapshots of what we've done. We also looked at other sources of ash other than fly ash, because fly ash, as we know, is going to be finished very soon. So we experimented with another type of ash that comes from sugar cane. So it's called processed bagasse ash. And we tested it as cement replacement. And we also tested raw bagasse ash as sand replacement. We also did a lot of work with small field site implementations. And I'm going to show you some of these, of the things that we've done in a second. But we also built finite element analysis model to predict the pavement performance and the fatigue life of the ECC pavements. Okay, so I'll start by giving more details about the low-cost ECCs that have fly ash and chrome rubber content. So this is a slide that shows the compressive strengths of regular ECC and chrome rubber ECC with cement replacement with fly ash and coarse sand and fine sand. So as shown in this slide, the ECC with coarse sand exhibited a higher compressive strength compared to the one with fine sand. This was the case for both the regular ECC and the chrome rubber ECC. In addition, replacing sand with chrome rubber caused a reduction in the compressive strength. This drop in the compressive strength of the ECC with chrome rubber is attributed to the defect-like behavior of chrome rubber in the ECC specimen. It's probably reducing the bonding within the cementitious matrix, in addition to the fact that rubber has a lower stiffness. We also saw that increasing the percentage of fly ash in the mix decreased the compressive strength. This can be attributed to the fact that the use of fly ash may limit the secondary hydration reaction of the fly ash at 28 days. We only tested at 28 days, but I believe that if we had left it longer and tested at 26 days, the compressive strength would have increased. This is a slide that shows some of the uniaxial tensile test results of regular ECC and chrome rubber ECC. An improvement was observed in the tensile ductility when we used the chrome rubber. We used 20% chrome rubber and it improved the ductility. With respect to the tensile strength difference between the coarse sand and the fine sand, as you can see, it was negligible. However, the use of fine sand enhanced the ductility. So some quick conclusions. We saw that increasing the content of cement replacement with fly ash increases the ductility of the composite. However, compressive tensile and flexural strengths were negatively affected. The chrome rubber produced a significant reduction in compressive strength and flexural strength, yet the formation capacity and strain were dramatically improved. The most important thing, we were able to develop PVA ECC materials that have a much lower fiber content. We went from 2 to 1.5 and 1.75 volume fraction, which drastically reduces the cost. And we successfully integrated local ingredients into these mixes. So ECC is now, cost is now more competitive and can be used as a replacement in concrete pavement applications. This slide compares one of the mixes that we developed, M3 at 1.5% volume fraction of fibers with regular concrete. And as you can see, it has 25% more compressive strength, 113% more flexural strength, 20% more tensile strength, and 31,900% increase in tensile string capacity, which is amazing. Okay, now I'm going to talk about the low-cost ECC that we created with Bagadash. So we're first looking at fly ash, and now we're looking at Bagadash. What is Bagadash? Bagadash is a byproduct of the sugarcane production, and it's a huge waste product in Louisiana. Globally, 0.76 billion tons are produced each year. Some of the sugar mills use it as a source of energy, but it's just a little bit, and everything else is a problem because it's a fire hazard and it needs to go to landfills. So we said, can we process this bagasse ash so we can actually use it in ECC? And we were thinking of two usages for the ECC. One as a cement replacement to reduce the content of cement, and one as a sand replacement to eliminate the river sand or the microsilica sand. So we had to process the sugarcane bagasse ash first. This is what the sugarcane from the mill looked like. We dry it at 65 degrees and then sieve it. And by doing that, we remove the coarse particles and you get what we call raw sugarcane bagasse ash. This is what we used as a sand replacement. If we further burned the raw bagasse ash at 450 Celsius for 3 hours and grinded it at 300 RPM for 35 minutes, we get what we call processed bagasse ash. And this is what we use as cement replacement. This is a quick picture showing backscattered electron images from SEM for both the raw sugarcane bagasse and the processed bagasse. The raw bagasse ash, as you can see, contains unburned fibrous particles, like you can see right here. By contrast, the processed bagasse does not contain any fibrous particles. They are similar, that you can see prismatic and irregular porous particles in both the raw bagasse ash and the processed bagasse ash. However, these particles are finer in the processed bagasse ash. Presence of these charismatic particles is attributed to a crystalline silica, while irregular porous particles are amorphous silica. We want to increase the amorphous silica as much as possible in the processed bagasse ash because that's what's going to make it more reactive in terms of cement replacement. Okay, so we also analyzed the composition of the raw bagasse ash and the processed bagasse ash using EDS. And as you can see from the analysis, the raw bagasse ash is mainly composed of silicon dioxide and carbon. Of course, the carbon comes from unburned sugars. But if you look at the pozzolanic components, which is the silica oxide, the aluminum oxide, and the iron oxide, in the raw bagasse ash, you get 52.6%, which makes it classified as a class C pozzolans according to ASTM. And for the processed, it increased to 83.9%, which means it can be classified as class F or N pozzolan, which is great. So that means the bagasse ash is not only it's not only something that can be used in ECC, but it also can be used in concrete as a cement replacement. The chart on the bottom side shows the strength activity index. As you can see from here, The processed bagasse ash met the minimum requirement, which is 75%. So it is suitable for being a replacement for the cement. Okay, this slide shows the compressive strengths of both the raw bagasse ash and the processed bagasse ash. The use of bagasse ash as a sand replacement, as you can see here, had minimal effect on the compressive strengths. In contrast, increasing the replacement of cement with the processed bagasse ash did reduce the compressive strength. Although we have a lot of amorphous silicon dioxide in the processed bagasse ash, which indicates that there is a high potential for pozzolanic activity, the observed decrease in compressive strength can be attributed to the strength activity index. We saw that it was more than 75%, but it's lower than 100. So still, it's not as high as can be. And the other thing is that since it's a pozzolanic material, we expect that it's going to take longer for it to reach its full strength because it takes longer. So there is the secondary hydration taking place that can exceed the 28 days that we're testing at. It can take months or years sometimes. Okay, this slide shows the tensile properties. And as we can see, the mix with 40% right here, replacement had the highest tensile strength with a small increase over the ECC control mix. As for the tensile strength strain capacity, we can see that replacing cement with the processed bagasse ash improved the ECC tensile strain capacity. The best performing ECC was the 50% cement replacement mixture right here. We also measured the surface resistivity for both the raw bagasse and the processed bagasse ash. All of the raw bagasse ECC exhibited lower surface resistivity when compared to control and fell in the moderate chloride ion penetration category. For the processed bagasse ash ECC mixture, their resistivity improved when compared to control, but all the mixes were in the high chloride ion penetration category. Maybe this can be attributed to the fact that the fibers in the matrix had hurted the pore structure, which allowed for ions to penetrate through the matrix. So, some conclusions. The most interesting part is that the raw bagasse ash and the processed bagasse ash both met ASTM standards to be used as a pozzolanic material. In general, compressive strength decreased with the increase in raw bagasse ash and processed bagasse ash. An improvement in the tensile ductility of 311% compared to control was observed in some of the mixes. The tensile strengths for all raw bagasse ash admixtures were higher than the control. An improvement of up to 85% compared to control was observed for ECC with 50% cement replacement with processed bagasse ash. So in conclusion, using raw bagasse ash as sand replacement and using processed bagasse ash as cement replacement is feasible, and that's going to reduce the cost of ECC drastically. Okay. So I'm not going to talk about the ultra high performance work that we're doing because I wanted to visit different technologies, but I'll show you some of the ECC field application that we've done at LSU. So when we started field implementation, we talked to facility services. All these people you're seeing are from LSU facility services. And we wanted to first try it in a place that does not have traffic. So we talked about sidewalks. The interesting thing about the LSU campus is that we have 100-year-old trees that have huge roots, and they break the sidewalks over and over and over again. Facility services is very frustrated with this. So we presented ECC as a solution because of its high ductility, and we installed it in a lot of the sidewalks. It has been there for 1.5 years. They don't even need to fix it. They loved it so much. They asked us to prepare some materials for them, and they use it for patching any cracks in the regular concrete all over campus. This is the mix that I was telling you about at the beginning, which is in front of the College of Engineering building. And again, it has been performing very well. We had a project where we wanted to do a full-scale testing in an accelerated loading facility. So we built an ECC pavement in the Louisiana Transportation Research Center Pavement Research Facility. And you can see this is the loading wheel right here. It's an ultra thin white topping over an asphalt pavement. And we have 3 sections, a 2.5-inch thick ECC, a 4-inch thick ECC, and a 4-inch concrete that's going to be used as control. All the sections are instrumented. So this slide shows the instrumentation that we used in the field study. We installed 3 different types of strain gauges during construction. The first 2 types were used at mid depths. And we put 2 of each sensor at each location for redundancy in case one doesn't work. The third type was placed at the bottom of the layer to make sure it doesn't move during construction. And as you can see here, we printed 3D supports for all the sensors so that they stay in place. This is a picture from the construction. So we had 3 companies working with us, concrete plant, Lemoyne construction company, and Icon. And we had workshops and webinars where we told them about the technology and how to mix it. Using their equipment, we also compared the mix that will come from regular construction equipment to what we're doing in the lab. And we constructed the pavement, and now we're waiting for LTRC to start the loading of the pavement so we can get some data on that. We have been doing collecting data on visual inspection. Okay, with that, I'm going to shift topics to this next technology that I want to talk to you about, and it's engineered geopolymer composites, or EGCS. This work is a collaboration between our group at LSU and the Material Science Department in Texas A&M, led by Dr. Miladen Radovic. So what are EGCs? EGCs are nothing but geopolymers-based ECCs. So why do we use geopolymers? The reason is geopolymers are better than concrete binders. If we compare them to Portland cement, we'll see that they have a faster strength development because polymerization takes place much quicker than hydration does. And it's more resistant to acid attacks and fire. And it's better at preventing corrosion of the steel reinforcement. In addition, it also has a much lower footprint because geopolymer produces much less CO2 emissions by 44 to 64% when compared to concrete. So why do we use it in ECC? If you remember the design criteria that I talked about to get the pseudo-strain behavior, hardening behavior, with EGCs, with geopolymers in general, the J-tip that is needed to attain the design is much lower at comparable compressive strengths. So it lends itself to engineered geopolymer composites. Okay, so how do we make it? You start with a geopolymer precursor and an activator solution. The geopolymer precursor is an aluminosilicate solution, and it can come from waste material like fly ash, slag, etc., or from natural materials like calcinated kalimatics. One example of that is the metakaline that we used in this project. The alkaline activator solution can be sodium-based or potassium-based, and we sometimes add to it alkaline silicate solution to increase the silica aluminate ratio. So what we were trying to do here is develop mixes, I'm sorry, is to develop mixes that can be used as engineered geopolymer composites. So we wanted to develop mixes that were metakaline based, and we're going to call them MK, or metakaline fly ash based, and that we're going to call MKFA. This work started a year ago, and we had our first publication at this TRB actually, and we are like, this work is going to continue with us for the next couple of years. But to design these mixes, we varied binder composition, aggregate types, and fiber type and content. So the ingredients that we used for that first project included the geopolymer precursor as either metakaline or a hybrid between metakaline and fly ash, and we used them as 50-50. The activator solution was potassium hydroxide and sodium hydroxide mixed with silicon dioxide. And we tested 2 aggregates, river sand and microsilica sand. And then we tested 2 fibers. We used the first fiber that we used for our ECC, which is non-oil coated PVA fiber. But that is still more expensive than ultra high molecular weight polyethylene fibers. So we wanted to experiment with these two. And that's when one more partner from Texas A&M, Dr. Svetlana, joined the group. And she, with her group, are developing the polyethylene fibers in their labs, which is really cool because I'm going to show you part of the results that's very interesting. This is very new. We have gotten the first result of this like a month ago, and it needs a lot more work, but it's very encouraging. Okay, can I just get a sip of water? Okay, so how do we make the EGCs? If we look at this chart schematic, we start by mixing the water, DI water, with the activator solution, either sodium-based or potassium-based with silicon dioxide, and we mix it at low heat for 24 hours until it becomes clear, and you can see right here. Once that happens, we start adding the metakaline or the metakaline fly ash, and then we put it in a whip mixer until it's completely homogeneous. That takes some time, between 15 and 30 minutes. That gives you the pure geopolymer. And then after that, you add the sand, whether it's river sand or microsilica sand. And then we add the fibers, whether PVA fibers or polyethylene fibers. And that's when you get the geopolymer mortar that we put in the molds. And when it cures, it becomes engineered geopolymer composites. We did a whole spectrum of testing, setting time, compressive strengths, uniaxial tensile test, flexural strengths. And now I'm going to show you some of the results. So the first thing is we were able to successfully produce the EGC mixes. We got pseudo-strain hardening behavior, as you can see in these. So this figure shows the results of the 28-day metakaline uniaxial tensile strength test. The specimen with the microsilica sand, right? You can see this one is a microsilica sand, presented the best tensile behavior by exhibiting a greater tensile strength and tensile strain capacity, but the river sand still worked, so they both can be used. This is the part that I was telling you about that's very interesting. So the polyethylene fibers that Svetlana is developing are actually working quite well. Let me go back here. And if you notice here, it's 2%. So the volume fraction here is 2% of the fibers. But we are only using 1% with the polyethylene. We are getting very encouraging results at a much lower volume fraction, which will reduce the cost drastically. And we are experimenting with both long fibers and short fibers, because the more that we can use existing fibers or low cost fibers, the more the cost of the EGCs will come down. So I'm very excited about this. Unfortunately, the metakaline fly ash combination did not perform well. As you can see, it's behaving like regular concrete. It gave us a single crack when we did the flexural performance test. So to date, this is not behaving like an EGC, but we are going to start working on varying the percentages of metakaline fly ash. As I said, this research was done at 50-50. We may end up doing 20% fly ash, 80% metakaline. So quick conclusions. The tensile pseudo-strain hardening behavior of metakaline-based polyethylene EGCs and PVA was superior to the PVA EGCs, but they both worked. The PVA specimens consisting of microsilica sand produced a superior tensile strength to that of the river sand. The opposite was observed with the polyethylene specimens in terms of ductility. The metakaline fly ash did not work. It did not produce pseudo-strain hardening behavior, so we cannot classify it as EGC, but we're going to work on that. Now, the last interesting technology that I'm going to cover is self-healing or self-rejuvenating asphalt. It's self-rejuvenating more than self-healing. And the whole idea is, as we all know, asphalt pavements age over time. So as a solution to this, we use rejuvenators or softening agents to reverse the aging of the binder. One of the problems with using rejuvenators and softening agents is that they do not penetrate through the depths of the pavement. So the whole idea behind this research was, can we place the rejuvenators inside the pavement during construction and it will automatically release the rejuvenator when needed as the pavement ages over time. Two mechanisms were tested in this research to deliver the rejuvenating product, microcapsules and fibers, and I'm going to give an overview of both quickly. So we start with the microcapsules. As you can see here, there is a urea formaldehyde shell that has the rejuvenator inside. It's mixed within the asphalt mixture. And when the asphalt starts to crack, it breaks the shell, releasing the rejuvenator, and it only releases a little bit at a time, so it does not soften the binder. We experimented with two different core materials or rejuvenators, a bio-based oil, sunflower oil, actually the one we use for cooking. It worked very well. And a synthetic one, which is known as Rejuve8. Okay, this picture shows an SEM picture of the microcapsules that we developed, and we are able to control the shell thickness, the diameter, the morphology by changing the parameters of the process with which we're creating the microcapsules, like the agitation rate. Then we measured the healing capacity. We prepared hot mix asphalt beams. We induced cracks in them and then left them to heal. And then after that, looked at how the cracks are closing over time, or the size of the cracks decreasing over time. And then we also measured the stiffness before and after to get the stiffness recovery. So as you can see, here is the beam being tested. It's a 3-point bending, stream controlled with a load rate of 0.25 millimeter per minute. The test was stopped 100 seconds after reaching the peak load. So it just induces a crack. The healing process took place over 6 days. We looked at the crack size using a light microscope on daily basis. And we measured, we put the specimens in two curing conditions, room temperature and high temperature, which is 50 degrees plus minus 2 degrees Celsius. And we calculated the healing efficiency. This slide shows the different mixtures. So we had control and then control with 5% RAS. Then we added the first rejuvenator to the 5% RAS. And then we added the micro-encapsulated rejuvenator to the 5% RAS. And then this is the sunflower oil with 5% RAS, and then microcapsules, sun oil with 5% RAS. And if you look at the crack, after 6 days, there is significant healing in all of the specimens, including the control. The actual healing efficiency agrees with what you just saw visually. And as you can see here, the rejuvenators are healing very well, whether the sunflower oil or the Rejuve8. The microcapsules are lower than the rejuvenator, and that's expected, of course, because not all capsules are going to break. But whatever capsules break are in the ones that are in the line of the crack. For stiffness recovery, you can see this is the original stiffness, damaged stiffness, and then healed stiffness. And as you can see, the sunflower oil had the highest stiffness recovery ratio, both at room temperature and oven temperature. Now I'm going to talk about the second delivery method, which is the fibers. These fibers are sodium alginate fibers. And again, this is a biodegradable natural material that is a waste material. The sodium alginate is polymeric in nature too, which gives an additional advantage. So why did we choose sodium alginate? It's inexpensive, it's organic, it's non-toxic, it has low impact on the environment. It self-degrades over time, which makes sense because it's going to release the rejuvenator over the service life of the pavement. And because it's a polymer, it may improve the elastic performance of the binder itself. So let me show you this video quickly. This is how we are producing these fibers in the lab. So we developed a synthesis procedure to prepare the sodium alginate fibers containing the rejuvenators. We used what we call a wet spinning process. That's what you're seeing in the video. The core material is the bio oil, the Rejuve8 that we just talked about with the microcapsule study. Inside this basin, there is a liquid. It's a coagulation paste that is made out of 0.6 molarity calcium chloride hexahydrate solution. So how do we produce these fibers? We take 5 grams of sodium alginate and dissolve them in DI water. And we also prepare what we call a polymeric surfactant solution, or PIMA. We do that by dissolving the copolymer in water at 70 degrees and mixing it for 60 minutes. Then we leave it to cool. The healing solution is mixed with the rejuvenator by different percentages by weight of rejuvenator. The PIMA is used for stabilization of the healing solution. And then we mix this mixture with sodium alginate a different rejuvenator to sodium alginate ratios at 40 RPM for 20 seconds. Once we have that, what you are seeing here is the solution in a syringe. It passes through the pass, and then you can see that we are collecting the fibers right here. This process actually gave us very good results. I'm just going to show a snapshot of the results like I've been doing. So this is results from the LWT. And as you can see, the rotting depth has improved drastically. So this is the control. This is the mix with 5% RAS, and this is the mix with 5% RAS and rejuvenator. For SCB, it also improved the fatigue cracking susceptibility over the mix with 5% RAP, as you can see here. For low temperature cracking susceptibility, we also see that the temperature is also almost the same for all of them, -16 to -17, but there is a large improvement in the failure load with the sodium alginate fibers. So in conclusion, the sodium alginate fiber reduced the stiffness effects obtained with recycled materials, which suggests that the rejuvenation effect is taking place. The SCB test showed that addition of the fibers improved the performance against fatigue cracking. And the addition of the developed fiber improved also the low temperature performance, as we have seen in the TSR-ST test. With that, I conclude my presentation. And I know I am a little bit over time, but we still have time for questions.
Thank you, Professor Hassan. Yes, I'll be checking if there are any questions. Oh, so I will start with Puneet.
Thank you.
Can I answer the question in the chat first?
Yes, sure.
So someone is asking whether I have a PhD in material science or CEE. And that's a nice question, but I want to tell you something. I've learned about the importance of multidisciplinary research. It takes quite a bit from both the student and the professor to talk the same language, to understand what other people are doing. But when you do, the results are astonishingly amazing. And I've worked with people from chemical engineering, material science, biological engineering, architecture, construction. And what you are seeing in the presentation is kind of the result of this collaboration. So don't be afraid of going out of your comfort zone. This is something I'm telling all the students that are in attendance, but that's why I wanted to answer the question.
Yes, thank you. Yeah, go ahead, Puneet.
Thank you, Professor. Lama, can you hear me?
Yes.
Professor, can you hear me? Okay.
Yes.
Thank you, Professor. This was a really great presentation. A lot of things to learn, especially the different kind of materials and everything. So I have a specific question regarding the micro capsules in the asphalt mixes you have proposed. So like I wanted to ask about the stability of these micro capsules first. And the second question was how these microcapsules were added. Were they added to the binder, or were they added to the mix, or at the process of mixing? So were they part of the binder, or they were added when the mix was being produced? So these are my two questions.
Excellent question, Puneet. So let me tell you that we went through a long process to make sure that the microcapsules and the fibers are stable. Remember when I showed you the SEM picture that we are able to control the morphology, the shell thickness, and the diameter of the microcapsules by varying the different conditions. And by controlling these things, in the end, we were able to create microcapsules that are stable, that are going to withstand the mixing process of the asphalt construction taking place. We added them first to the binder and mixed them, and then added the binder with the microcapsules to the mix, and then mixed it again.
Thank you, Professor.
By the way, I mean, I did give a snapshots of different technologies, but if you're interested, just shoot me an email and I'll send you some publications that has all the details.
That will be great. Yeah, that will be great. Thank you so much.
My pleasure.
And now, Professor Professor Ahmed.
Hi, yeah, thank you for a really nice presentation, Marwa. It was really great to see so many different projects. I have kind of two questions. I guess the first one is a very specific question about the fibers that you presented at the end. Did you guys compare with just like an SBS modified binder? Because it seems to me this material was kind of having a very similar result to using an SBS or some kind of elastomer. And the second question is, I guess, a little bit more broad. In terms of, you showed the bagasse ash results. Is this a scalable technology? Because it seems to me like we're not producing much sugarcane in the US, maybe for other countries, but I know you guys are working heavily on the implementation. Is this a technology that we could scale up in construction?
I think okay, let me answer the fiber question first, and then I'll go to the bagasse. I was going to jump over that. So the control mixes, if you noticed for the sodium alginate were PG 70-22, which is polymer modified. It doesn't have SPS, but it is polymer modified. So yeah, and the main reason for using the fibers is not to get better elastic behavior, although it helps with the elasticity and the ductility of the binder, but it's a solution to deliver the rejuvenator to the depths of the pavement and reverse the aging process. I gave a snapshot. We did crack analysis work similar to what we've done with the microcapsules, and we have done stiffness testing. I just wanted to show different results for the microcapsules versus the sodium alginate for the sake of time. But again, I can provide the papers and you can see that. For the bagasse ash, I believe that there are states like Louisiana and many others in Region 6 that produce a lot of bagasse ash that can be scaled towards implementation. There are some states in the US that don't have it, but it can be a supplemental product when used as a replacement for fly ash. We are running out of fly ash. Maybe it can be used with fly ash, and that's one way to scale it.
Thank you.
Now we have a question from Javier.
Yes, hello, Professor Marwa. Thank you for this very nice presentation. I know it wasn't the focus or the main focus of the presentation, but I was interested in knowing about the photocalytic covering and more specifically how it affects aging of the binder and the structural performance of flexible pavements.
Oh, Javier, we have done tons of work on that. And again, if you email me, I can send you publications. So nano titanium is not going to negatively affect the performance of the pavement, whether it's asphalt or concrete at all. Actually, I was worried about asphalt pavement specifically because what nano titanium does is that it uses UV rays to oxidize inorganic material. So, organic material. So, but the binder falls under this category. So I was worried about it affecting the properties of the binder, and we got NSF funding that just looked at that. There is a definite, very slow reaction taking place in asphalt pavements, but it's very slow that it passed all super paved PG grading tests. Again, you can email me and I'll shoot you 3-4 papers, and then we can have a longer discussion.
Thank you. I will.
Sure.
Okay, so I have many more questions in the chat box. I'll try to ask as many as we can. So I have a question from Deb Mishra. It says, what are the energy implications of the processed bagasse? They had to burn the raw material for 3 hours. Is that going to require significant energy consumption in the field?
Well, actually, so that's why we developed 2 levels of bagasse, right? The raw bagasse does not require much energy to burn at all. It's a very quick process that can easily be done, but that's hand replacement. The long burning process and the slow long burning process is to increase the amount of amorphous silica that are available, to increase the activity in the processed bagasse ash. And yes, we need to build facilities that are capable of processing. But the way I see this being implemented is that you've got the sugar mills. The sugar mills do have the capabilities of burning the bagasse, but it's not controlled burning. So that's the difference. If this becomes something that we're going to use on a global scale market, if they can adjust their furnaces, like modify the infrastructure, so the processed burning happens in the sugar mills, then the sugar mills would be the ones that are selling the bagasse ash. It would be like achieving two goals with one step, and it would be ready for full-scale implementation.
Another question from Professor Al-Qadi. He says, Geopolymer has been successfully used in Australia. The difficulties in the US is the cost effectiveness and the time to cure. Do you have any thoughts about that?
Yes, absolutely. And geopolymers is still being studied as a replacement for concrete. We are working on the cost. So a lot of what I presented today is to reduce the cost of the geopolymer and the engineered geopolymer at the same time. If we're able to reduce the content of the metacolline, that's going to be very useful and very drastic. The other thing is, if we go away from geopolymers and go to engineered geopolymers, and it's an advantage to ECC as well, the performance that we are getting from them, whether it's compressive strength, flexural strength, tensile strength, is so good that the needed sections thickness will be reduced drastically. For example, the ultra thin white topping that I showed you that we have built in the ALF facility is 2.5 inches, which is drastically small, and it's performing very well. So if we're reducing the needed sections by half or sometimes by a quarter, then the cost is there. The other part of it is eliminating all the joints, whether it's EGC or ECC. The amount of cost that's going to be reduced by eliminating construction joints from the construction cost itself is going to make EGC and ECC more cost effective. We did a preliminary cost analysis looking at the initial cost of materials and construction, and with our low cost mixes, it's equivalent to existing concrete pavements, which is kind of amazing.
Yeah, sorry to tire you with questions. I think that everyone has questions.
Thank you guys for being interested.
Yeah, so Professor Jeff Rosler has two questions. He says, dimensional stability of ECC, which has huge paste volume, he's questioning that. And also the ability to mix ECC with 1.5% PVA in practice, which requires higher shear capacity mixes.
Okay, so the lowest volume fraction that we were able to get to work in ECC was 1.5, not 1%, right? We developed construction processes. We actually installed the 1.5% mixes that are in the ALF and in LSU using regular concrete mixing equipment. We have optimized the time that we need to mix them and what happened at the concrete plant. We went to the concrete plant ourselves and we put the ingredients and we made sure that there was quality control process. We published a paper in CRR that summarizes all of these quality control processes, but we were able to attain that. The 1% that I was talking about is with polyethylene, ultra high molecular weight polyethylene fibers, and it's in EGCs. And this is like really brand new. I'm just showing you results that we are still discussing in the research group.
Yep. Well, I have more questions, but for now, thank you so much for the amazing presentation, Professor Hassan. It was really nice to have you. And we have to end on time, but thank you so much. And Noel has the link for the announcement. You can all please join that. Thank you so much, Professor.
Thank you for having me, guys, and please reach out by email if you have any questions. I'll be very happy to continue the discussion.
Oh, you will have many emails. Thank you, Professor.
Thanks, Marwa.
Thank you. Bye, everyone.
Bye.